This is problem 13.134. It's on page 877. An estimate of the expected load on over-the-shoulder seat belts is to be made before designing prototype belts that will be evaluated in automobile crash tests. Assuming that an automobile traveling at 45 miles per hour is brought to a stop in 110 milliseconds, that's 0.11 seconds, determine A, the average impulsive force exerted by a 200-pound man on the belt, and B, the maximum force exerted on the belt if the force time diagram has the shape shown. We'll draw that in part B, the force time diagram, but let's start with the first part. So we're given some information, and that is the initial velocity, 45 miles per hour. The final velocity is, of course, 0 because we're bringing the person to rest. The person's mass is 200 pounds mass. And the time is 110 milliseconds. As I said, that's the same thing, because milli is 10 to the negative third. That's the same thing as 0.11 seconds. Okay? And we'd like to find the average force. I guess I'll go ahead and draw the diagram they gave. They'd also like to know the maximum force if instead of having just this average force, rather the force versus time characteristics look something like this. We have time here, force here. The force would ramp up to some level. We don't know exactly when it ramps up to that level, and then how it decreases. It doesn't really matter, but the amount of time is 110 milliseconds in both part A and B. And obviously the force will reach some maximum force here. We don't want that force to be too large, or else we damage the person, the 200-pound person that we're trying to save. So let's start with impulse momentum, because obviously they gave us time and force, so therefore impulse momentum is our natural go-to. The initial velocity, or the initial momentum, plus the force, or the impulse of the force that brings the body to rest, because after all, the body has no momentum in the final state, is represented by this equation. So then, if we rearrange things just a bit, if we take the integral term to the other side and try to take the force out, well, the only way we can do that is if the force is a constant, right? So that would mean that we're really getting at the average force. And I need to be careful here. Okay, so, well, I'll show you. So this force, notice that I have drawn the momentum in a certain direction. Really, this is a vector equation, right? So if the person is moving to the right, then they have momentum to the right. Now, obviously, the force acting on them must act in the opposite direction, but notice I've implicitly assumed that the force is acting to the right. Now, not surprisingly, just like in free body diagrams, when you have an unknown force, if you solve for the force and you find that it's negative, you've assumed the wrong direction. So you'll see it come out that way here as well. Anyway, so taking the force out of the integral gives us an average force, and then we just have the integral dt. That's just the time then that is required to bring the body to rest. So if we solve for the average force, then what we'll get is negative mv naught over t, and that is negative 200 pounds mass times 45 miles per hour times 5280 feet per mile times 1 hour per 3600 seconds. Okay, that's just the mass, and then, oh no, that's the mass and velocity, divided by time, which is 0.11 seconds. Okay, so notice that what we'll get out of this, the units we'll get, are pound mass, feet per second squared. That's not what we want. We want pounds force. So what we need to do is convert it. So it takes 32.2 pound mass feet per second squared to equal 1 pound force. So what's happened? Well, I put this conversion factor in the denominator. Notice what that does is that means that I'm canceling things, right? Because you would really invert and multiply, okay? So if something's in the numerator of the denominator, then it's really in the denominator. It cancels with something in the numerator. Same thing with the feet, same thing with the seconds, except notice there's 1 second here which cancels here, and a second there that cancels there. So we're left with units of 1/1 pounds force, which are just pound force. Anyway, this comes out to negative 3,726.7 pounds force. So, of course, my assumed direction of force is wrong. In other words, the force is actually pointing against the direction of motion. Okay, but there's the numerical result. That's how much force, on average, must be applied to the person, which is quite a lot. I'm not sure that we want to provide or apply over a ton of force, right? Almost 2 tons of force on the person's body. I'm not sure that would be good for the person's body. I don't know what a body can take. But there's part A. Part B says, okay, what if we apply the force where we start off with no force, it ramps up and then ramps down? Now this is reasonable because if you think about it, when the person is being brought to rest rapidly, they're going to tend to try and move forward, right? Their body can move relative to the vehicle. So the seatbelt tension is not going to grab at the very beginning. It's going to grab somewhat gradually as the person's body leans into the seatbelt. Okay, so that's why this shape seems somewhat reasonable, at least for a beginning process. Now, if we think about this force versus time, what does the area beneath this graph represent? It represents impulse. It's basically this term, isn't it? Right? So it's just area. So how much area is this? Well, this is just a triangle, isn't it? So the integral of that force over time would just be 1/2 the maximum force. Notice it doesn't matter where this maximum occurs, but 1/2 the maximum force times the time. So the base times height over 2 really is all we've done, right? Now, of course, the time is 0.11 seconds. Let's see, it looks like oh, yes. Yeah. But notice we already know how much impulse is required, right? Because if we rearrange this equation, as we did, really this F times T, that represents the magnitude of the total impulse required to take this mass from a momentum that it has initially to no momentum. So this must be equal to the average force times time, right? Because we already know that this is the impulse. So we can cancel time across, of course, it's no longer equal to F dt, but you get the idea. So basically, the maximum force would be 2 times the average force. So that is about negative 7,453.4 pounds, just sticking with my original assumption of the direction of force. This obviously would be in the opposite direction as well, against the direction of the momentum or against the direction of the velocity. But if the seatbelt doesn't apply the force continuously and it has to ramp up, it looks like we could have a whole lot more force than almost 2 tons. This is almost, what, almost 4 tons, right? Which doesn't sound like a good idea to me.